Hello again. Okay, so you were supposed to have tried this piecewise function, but in case you didn't, I do want to walk through it. Well, even if you did, I do want to walk through it with you guys. Okay, so remember with these functions, they all have such specific shapes that we need to write out the transformation chart, find out where the domain restrictions exist, and then try to graph the function as is. So, for example, the first one I'm going to do in blue, there isn't a b value, which is great. So that means it's x minus 4. And I say that's great because that means there isn't any extra parts of the function we need to watch out for as far as transformations. Okay, and then we have negative 1/4 y minus 6. Now, just like I did last time, although this is a cubic function, not a cube root function, so we still have 0, 0 as the center, but it's going up like that, okay? Keep the shape in mind for later. Our parent function points are negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. Okay, so if we take those x values and substitute them in, negative 2 minus 4 gives us negative 6. Negative 1 minus 4 is negative 5. And then fill in the chart with me, if you haven't already. For negative 8, if we substitute that in, negative 8 times a negative 1/4 is 2. 2 minus 6 gives us negative 4. Negative 1 times negative 1/4 is 1/4. Minus 6 gives us negative 5 and 3/4. 0 gives us negative 6. 1 will give us a negative 6 and 1/4. And then 8 will give us a negative 8. Okay, now looking at the restrictions, it needs x to be less than negative 2, which is great because we're going to include all of these points. And at x being negative 2, I'm going to write that it is an open circle so that we can remember when we go to graph. For the middle function, I'm going to do it in orange, and that is a greatest integer function. So I'm not going to make an x and a y chart. I am, however, going to factor out the b value, so we get x minus 2. And I'm going to acknowledge that a is 2, which is the distance between the steps. B is 1/2, which implies that the length of every step is 2. And then the starting point is at HK, which is 2, negative 4. And I know that's a little bit unorthodox from what we have done in the past, so bear with me. If you're like, what's she doing? Hang in there. All right, for the last piece, it's the absolute value function. So I'm going to write x plus 7 because that's our h value. And then negative 4y plus 8. Again, the parent function's points would be negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. I'm going to go a little bit faster because you were supposed to have done this already. If you need to, you can always pause. So plugging in the x values, we would get 5, 6, 7, 8, and 9. For the y values, we would get 0, 4, 8, 4, and 0. Now, its restrictions go from negative 6 to 9, so 5, 0 is not included. We would include all of these values. At x being 6, it is a closed circle. At x being 9, it is an open circle. All right, let's do it. I'm going to graph the first piece, remembering what the function shape should look like. Our central point is going to be at negative 4, negative 6. So I'm going to go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, closed point. I'm then going to graph 3, to the best of my ability, of course. Negative 3, negative 6 1/4. And negative 2, negative 8, when that is an open circle. Oops, that's 9. There we go. And then negative 5 3/4. And negative 6, negative 4. 1, 2, 3, 4. There we go. So from that central point, I curve down and then I curve up, and it goes on forever because there's only one restriction. We only have one restriction rather than bookends. For the middle part, with the greatest integer, this might be where we tripped up a little bit. My recommendation for the greatest integer is to graph it and then erase what you don't need. Because we don't use our X and Y chart, so it's a little bit different, right? We start at 2, -4. So at 2, -4, 1, 2, 3, I have a closed point. Remember, your restrictions go from -2 to 6. So 2 is within the domain. The length of my step is 2 units. There is not any sort of reflection. So I go 2 units over and open circle. If it helps, go 1, 2, 3, 4, 5, 6, go to 6 and draw a dashed line, as well as -2, because those are the restrictions for this particular domain. So that might visually help you to see where your steps should stop. Just a suggestion. Okay, A is 2, which means I'm going to go up 2 units, extend out to the right, open circle. Boom! I am now at X being 6. X is required to be less than, not equal to. So an open circle is appropriate. And working backwards, I go down 2. And then another down 2. Oh, and this is going to overlap. That is okay. One is an open circle, one is a closed. So that's neat. And you're like, neat? Really? Yes, that's neat. That's great. All right, last but not least, absolute value. We have the vertex included, so let's graph that first. 1, 2, 3, 4, 5, 6, 7, and up to 8. And then we go down to 6, 4, and that's a closed circle. We know that that's going to connect in a straight line because it is an absolute value function. And then 8, 4, and at 9, 0, it's an open circle because the domain restriction tells us so. Woo! That's what it should look like. All right, we know that this is not continuous. How do I know that? Because there are gaps between the pieces. You cannot draw this really cool looking function from one side to the next without lifting up your pencil. Sorry. The domain goes from -infinity because of the parabola all the way over to 9, non-inclusive, because it's an open circle. The range starts all the way down at -8. But again, because of that parabola, it's going to shoot up to infinity. Hopefully you guys got that right. If not, please write down some questions and ask me so we can clear that up together, okay? Alrighty. I don't know what that is up there. Can I erase it? All right. Bear with me as I pull. I know. You're like, why are you doing this now, Patterson? Because it's driving me crazy. All right. We are going to cover this last part, absolute value functions as piecewise. Now, one skill that you need in calculus is to be able to tear apart an absolute value function into 2 linear functions. Okay, so take, for example, this guy. The absolute value of X, right? So if I were to graph it, just my little sketch here so we can get the visual, it looks like that. But if I were to split it, it actually splits at the vertex. This is -x, that is X. And we say that one of them is less than 0 and the other is greater than or equal to 0. Now, does it matter which one has the equal to? Nope, does not matter. So that's why it says, notice that really either inequality could have the equal to, but it is convention for the greater than. Now, am I going to mark you off because you chose the less than? No, absolutely not. But know that you have the choice. Okay, you have the choice. I'm going to skip this part for right now. I just want to jump into it. So we are going to be asked to write an absolute value equation as a piecewise. Easy peasy. First thing, does this open up or down? It opens up. So we need to acknowledge where it opens. Second, we need to find the vertex. Okay, In order for me to do that, for the given example, I need to factor out the b value. So I get 3 times the absolute value of 2 times the quantity x minus 1 minus 1. So our vertex is at 1, negative 1. Step 3, I'm going to sketch what this function looks like so that I have some sort of an idea of my positive versus negative sloped areas. Okay, notice for our example up here, the restrictions were set at the vertex, at the axis of symmetry specifically. You might want to write that down. The axis of symmetry is going to separate our pieces. So, since our axis of symmetry is x equals 1, 1 is going to define our piecewise domain restrictions. Okay. Step 4, we need to find the pieces. Well, we know that the piece on the left and the piece on the right, I'm using a lot of numbers. Oh, and I just deleted half of my, there we go. Sorry. Let's just call it A and B, okay, so we don't get confused. In order to find the pieces, notice they're linear. One has a negative slope and one has a positive slope. We are going to create two equations, one with a positive slope, and notice I got rid of the absolute value bars and I went back to the given. The other has the negative slope and I drop the absolute value bars, I go back to the given. The purpose is so we can find those linear equations for the left part of the vertex and the right. Just simplify with me, please. Distributing the 3, we get 6x minus 6 minus 1. Combining like terms, we get y is equal to 6x minus 7. And since it has the positive slope, this corresponds to the b. That's why this sketch is so important. For the right-hand side, or the right equation, I'm going to distribute the negative 3. So negative 6x plus 6 minus 1. Don't forget to distribute that negative, you guys. So we get negative 6 plus 5. Because this has the negative slope, and please don't forget the x like I just did, this corresponds to the left-hand side. Okay, I know I got a lot of highlighting going on here. Let me see if I can calm it down. All right, so step 1, step 2, step 3, step 4. We are now entering step 5, the grand finale, where we are going to write our piecewise equation. There is only one f of x. Please do not write f of x and then y. Oh, redundancy. Oh, a little bit of me cries. Don't be that person. All right, the left side with the negative slope, which again is why that sketch is so important. The negative slope goes first. So negative 6x plus 5. That's the equation for the left side of the absolute value function. The second piece, the b, the right side of the axis of symmetry of the vertex, has the positive slope. That is 6x minus 7. We're then going to write the restrictions based off of the axis of symmetry. Again, it doesn't matter which one you put the equal to. One of them has to have it, one of them can't have it, because they intersect at the same point. If they're both closed points at the same x value, it is no longer a function. Eek! We can't have that. So choose one. Again, I don't care which. Normally, conventionally, it's the greater than. So we'll say x is less than the axis of symmetry, which is 1, and then x is greater than or equal to 1. Again, if you put that it's less than or equal to 1, I will not mark you wrong. Hopefully we're good. If you have questions, write them down. Ask me. I want you to try these, and what I'm going to do is I'm going to pause the video, and then I'm going to do the answer key for you, and then I'll unpause. So with me right now, please pause this, try A, B, and C, and then hit play. All right, so here is A. Notice it opens up, so the negative slope piece is on the left of the axis of symmetry, on the left of the vertex. So I wrote some little notes. Again, make sure there's only one f of x. There's only one x equals. It's super redundant, unnecessary, wrong if you are listing f of x and then y. And as far as the inequalities are concerned, one of them needs to be equal to and the other needs to not. Okay, for b, we had to factor out the b value and notice that it was down, okay? Two differences. So now the positive slope is to the left. Sorry, that was bugging me. There we go. And the negative slope is to the right of the axis of symmetry. For C, not only did I rewrite it so that the t was in front, the t is the variable, it's the input. It's okay that it's not an x value. But then I had to factor out the b value and so forth. So hopefully you guys got this right. Again, if you have questions, write them down and ask. All right, good luck on your homework.